November 29th, 1945. Tachikawa Air Base, west of Tokyo. A Douglas C-54 Skymaster transport aircraft touched down on the scarred runway, carrying a cargo that would shake the foundations of Japanese aeronautical confidence. Inside the fuselage sat components of a Boeing B-29 Superfortress, carefully disassembled and catalogued by American occupation forces before being released for Japanese examination. The aircraft had been shot down over Japan months earlier, and what remained of it represented technology so advanced that Japanese engineers would spend the next 18 months trying to comprehend how far behind they had fallen. The bomber wasn't just a weapon, it was a declaration of industrial supremacy that made Japan's most advanced aircraft look like relics from another era. The story actually began 3 years earlier, in the summer of 1942, when Japanese intelligence first received reports of a new American bomber under development. Reconnaissance photographs showed a massive 4-engine aircraft being tested in Kansas, larger than anything Japan had encountered. Initial assessments dismissed the threat. American bombers had proven vulnerable to Japanese fighters. The Mitsubishi A6M-0 had dominated early Pacific air combat, shooting down B-17s and B-24s with relative ease. Japanese military planners assumed any new bomber would simply be a larger target. They were catastrophically wrong. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. On June 15th, 1944, the reality arrived over Yawata Steelworks in Kyushu. 47 B-29 Superfortresses struck Japan for the first time, flying from bases in China. Japanese fighter pilots scrambled to intercept, confident in their experience and aircraft. What they encountered instead was humiliation. The B-29s flew at altitudes their fighters struggled to reach. When Japanese pilots finally climbed to intercept altitude, their aircraft handled sluggishly in the thin air, unable to maintain speed or maneuverability. The bombers' defensive armament, coordinated through a revolutionary central fire control system, created overlapping fields of fire that shredded approaching fighters. Pilots who survived the encounters returned with reports their commanders initially refused to believe. The new American bomber was untouchable. Lieutenant Commander Takeo Shibata, a veteran Zero pilot with 11 confirmed victories, filed a combat report after engaging B-29s over Osaka in December 1944 that captured the desperation Japanese aviators felt. "We approached from the stern. Standard attack procedure," he wrote. "At 400 meters, their tail guns opened fire with accuracy I have never witnessed. The tracers appeared to track us individually. I broke left. My wingman broke right. Both of us took hits. I watched my wingman's Zero disintegrate. I dove away, my aircraft trailing smoke. I climbed back to attack altitude. It took 12 minutes. The bombers were gone. We were children throwing stones at armored vehicles." Shibata survived the war and later became an aerospace engineer. He spent decades studying the aircraft that had so thoroughly outclassed him. The technical specifications of the B-29 seemed impossible to Japanese engineers who studied intelligence reports throughout 1944. The bomber's maximum takeoff weight exceeded 70 tons. Its pressurized cabin allowed crews to operate at altitudes above 30,000 feet without oxygen masks. Its 4 Wright R-3350 engines, each producing 2,200 horsepower, drove the massive aircraft at speeds exceeding 350 miles per hour. Its range extended beyond 3,000 miles, carrying a 5-ton bomb load. Every specification exceeded Japanese capabilities by margins so wide they suggested American industry operated under different physical laws. Japanese aircraft designers had attempted to create high-altitude bombers. The Nakajima G-10N Fugaku project envisioned a 6-engine monster capable of bombing America's west coast. Engineers produced detailed drawings and specifications They calculated performance parameters and designed production facilities. The project never advanced beyond paper studies. Japan lacked the industrial capacity to build the engines, the aluminum alloys for the airframe, the precision instruments for navigation, and the sophisticated systems integration the design required. The Americans had not only designed such an aircraft, they were producing it in quantities that darkened Japanese skies daily. When a damaged B-29 made an emergency landing on Soviet territory in 1944, Japanese intelligence officers lobbied desperately for access to examine it. The Soviets, technically neutral in the Pacific War, refused. Joseph Stalin understood the bomber's value and would eventually order his engineers to copy it completely, creating the Tupolev Tu-4. Japanese engineers would have to wait until their own forces brought down a B-29 over home territory. That opportunity came sooner than expected, though not in circumstances Japan would have chosen. Throughout late 1944 and early 1945, American bombing raids intensified. Major General Curtis LeMay, commanding the 21st Bomber Command, shifted tactics from high-altitude precision bombing to low-altitude incendiary attacks. On the night of March 9th through 10th, 1945, 334 B-29s attacked Tokyo with incendiary bombs, creating firestorms that killed over 100,000 civilians and destroyed 16 square miles of the city. The raids came night after night, burning Japan's cities systematically. Osaka, Nagoya, Kobe, Yokohama, all burned. Japanese air defenses proved utterly inadequate. Fighter pilots developed kamikaze tactics specifically targeting B-29s, deliberately ramming the bombers when ammunition ran out or guns jammed. The sacrifice occasionally brought down a Superfortress, but American production replaced losses faster than Japanese pilots could inflict them. Every downed B-29 represented a temporary victory purchased with a pilot's life, a pilot Japan could not replace. The mathematics of attrition warfare had become brutally simple. America could afford its losses. Japan could not. In April 1945, a B-29 designated Z-35 from the 313th Bombardment Wing suffered catastrophic engine failure during a raid on Osaka. The aircraft, piloted by Captain James Ryan, fell behind its formation, losing altitude as its crew struggled to restart the failed engine. Japanese fighters swarmed the straggler. Anti-aircraft fire hammered the damaged bomber. Captain Ryan attempted to reach the ocean, hoping to ditch where air-sea rescue could retrieve his crew. His aircraft disintegrated 3 miles from shore, breaking apart as it hit the water. 8 crew members died in the crash. 2 survived. Captured by Japanese naval forces within hours. Naval salvage teams located the wreckage in relatively shallow water. Despite fuel shortages and collapsing logistics, the Japanese Navy devoted resources to recovering the bomber's remains. Divers worked for 2 weeks, bringing up major components. The center fuselage section came up largely intact. 3 engines were recovered, damaged, but potentially rebuildable. Critical avionics, fire control computers, and sections of the pressurized cabin arrived at Yokosuka Naval Arsenal by late May 1945. Japanese engineers finally possessed tangible evidence of American technological superiority. They had perhaps 3 months to study it before Japan's surrender rendered the examination academic. The initial assessment team at Yokosuka included some of Japan's most accomplished aeronautical engineers. Captain Shiro Kawamoto, who had designed components for the Kawanishi H-8K flying boat, led the structural analysis group. Commander Jiro Horikoshi, designer of the legendary Zero fighter, headed the aerodynamics team. Dr. Takeo Doi, Japan's leading expert on supercharger technology, examined the propulsion systems. Each engineer brought decades of experience. Each would conclude that Japanese aviation technology had fallen behind by a margin measured not in months, but in years, perhaps decades, in certain critical areas. The examination began with the engines. The Wright R-3350 duplex cyclone represented 18 cylinders, arranged in 2 rows, displacing 3,350 cubic inches. Japanese engineers had nothing comparable. The most powerful Japanese engines, the Nakajima Homare and Mitsubishi Kasei, displaced barely half that volume and produced significantly less power. Dr. Doi's team disassembled one of the recovered engines completely, measuring every component, documenting every design feature, attempting to understand how American engineers had achieved such power output reliably. What they discovered went beyond mere displacement. The R-3350 incorporated features Japanese engineers had attempted but never successfully implemented. Sodium-cooled exhaust valves prevented valve burning at high power settings. Japanese engines suffered chronic valve failures. The Americans had solved it through materials, science, and innovative design. Sophisticated fuel injection systems replaced carburetors, improving mixture control and allowing the engines to operate inverted during combat maneuvers. Japanese engines still used carburetors that starved during negative G maneuvers, a vulnerability zero pilots had learned to avoid through tactics. The Americans had eliminated the problem through engineering. The propellers proved equally sophisticated. Hamilton Standard hydromatic constant-speed propellers automatically adjusted blade pitch to maintain optimal engine RPM, regardless of airspeed or altitude. Japanese propellers required manual adjustment, demanding pilot attention and reducing efficiency. The American propellers included feathering mechanisms, allowing pilots to stop windmilling on failed engines, reducing drag dramatically. Japanese propellers lacked feathering capability, meaning engine failures created massive drag that often doomed aircraft. Dr. Doi's team measured tolerances in the engine components with instruments salvaged from bombed factories. What they found was precision that Japanese manufacturing could not match even in peacetime, much less under wartime conditions. Piston-to-cylinder clearances, measured in 10,000ths of an inch, remained consistent across multiple cylinders. Crankshaft journals showed mirror-polished surfaces free of tool marks. Connecting rod bearings displayed perfectly uniform surfaces. Every component spoke of manufacturing processes Japanese industry had not mastered. The pressurization system astonished engineers who examined it. Maintaining cabin pressure at altitude required sophisticated sealing systems, pressure regulators, and structural design far beyond anything attempted in Japanese aircraft. The B-29's cabin pressure differential allowed crews to operate at altitudes above 30,000 feet while experiencing conditions equivalent to 8,000 feet elevation. Crews could work without bulky oxygen equipment, could eat and drink normally, could communicate easily. Japanese bomber crews at high altitude wore layers of heated suits, struggled to breathe through oxygen masks, suffered frostbite and hypoxia. Commander Horikoshi's structural analysis team documented construction techniques that revealed systematic production methods Japanese factories had never achieved. The B-29's fuselage skins were formed on massive hydraulic presses, using dies that cost more to produce than some entire Japanese aircraft. Once those dies existed, however, workers could stamp identical panels at rates impossible through hand forming. Every panel from the production line matched specifications precisely. Installation required no fitting or adjustment. Rivet holes aligned perfectly between skins and stringers because both components were manufactured to tolerances that guaranteed proper fit. The remote-controlled gun turrets represented technology Japanese engineers had theorized about but never successfully implemented. The B-29 mounted 5 turrets, each containing 2 50-caliber machine guns. Gunners sat at fire control stations inside the pressurized cabin, operating the turrets through a computing gun sight system that calculated lead angles automatically. The system accounted for airspeed, altitude, temperature, and ballistics. Gunners simply placed the reticle on the target and fired. The computer did everything else. Japanese bombers mounted manually aimed defensive guns, requiring gunners to expose themselves to freezing, oxygen-poor conditions in open positions. Accuracy depended entirely on the gunner's skill and ability to estimate lead angles mentally while fighting hypoxia and frostbite. The American system removed human limitations from the equation through technology. One B-29 gunner, properly trained on the fire control system, could achieve accuracy no Japanese gunner could match, regardless of experience or skill. The central fire control system allowed any gunner to take control of any turret. If one gunner was wounded, others could defend his sector. The system could slave multiple turrets to a single gun site, concentrating fire from multiple positions on a single target. Japanese designers had proposed similar systems in 1941 and 1942. Prototypes failed repeatedly. The necessary computing mechanisms required precision manufacturing and electronics Japan could not produce reliably. The Americans had solved problems Japanese engineers knew existed but could not overcome. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The radar systems recovered from the wreckage opened entirely new areas of technological inadequacy. The B-29 carried multiple radar sets for different purposes. APQ-13 radar provided navigation and bombing capability, allowing crews to identify targets through cloud cover or darkness. APQ-7 Eagle radar offered even higher resolution for precision bombing. Tail warning radar alerted crews to fighters approaching from behind. Japanese aircraft mounted no operational radar systems. Night fighters relied on visual acquisition, searchlights, and luck. Engineers at Yokosuka attempted to power up the recovered radar sets using captured American generators. The systems refused to function, damaged by immersion and rough handling during salvage. Technical manuals recovered with the wreckage revealed capabilities that seemed like science fiction. The bombing radar could identify individual buildings in cities from altitudes above 20,000 feet. The navigation radar could map coastlines and terrain features, allowing crews to navigate precisely without visual references. Japanese bombers navigated using compasses, charts, and celestial navigation when weather permitted. The Americans had relegated human navigation to backup status, trusting electronics to guide their bombers. The electronics throughout the aircraft revealed sophistication far exceeding Japanese capabilities. Miniaturized vacuum tubes, printed circuit boards, and standardized components filled racks and panels throughout the pressurized sections. Japanese aircraft electronics relied on hand-wired point-to-point connections prone to vibration failures. American electronics used plug-in modules designed for rapid field replacement. A technician with basic training could replace an entire radio or radar unit in minutes. Japanese electronics repairs required skilled technicians who could diagnose failures and repair individual components. Captain Kawamoto's team, examining the airframe structure, discovered construction methods that explained how American factories achieved production rates Japanese plants could never approach. The B-29's wing used a box beam structure with machined spars running the entire wingspan. Each spar was machined from aluminum forgings on automated equipment, requiring no hand-fitting or adjustment. Japanese wing spars were built-up structures assembled from multiple pieces by skilled workers who fitted each component individually. The Americans had invested enormous resources in tooling and equipment that enabled rapid production. Boeing's Wichita plant alone produced over 1,600 B-29s during the war. Martin's Omaha facility built more than 500. Bell's Marietta plant contributed over 600. Total B-29 production exceeded 3,700 aircraft in just over 3 years. Each bomber contained over 50,000 individual parts, every one manufactured to specifications, allowing assembly without custom fitting. Japanese engineers calculated that producing even 100 B-29s would require retooling their entire aviation industry, training thousands of new workers to higher skill levels, and importing machine tools and materials Japan could not manufacture domestically. Production would take years to reach even minimal rates. By comparison, American factories were producing multiple B-29s daily across 3 production lines. The industrial capacity gap wasn't measured in percentages. It was measured in orders of magnitude. The examination revealed other details that spoke to systematic American advantages. The bomber's oxygen system included regulators manufactured by automobile parts suppliers, companies with no aviation experience who simply applied their existing precision manufacturing capabilities to aircraft components. Japanese aviation suppliers were specialized firms that had developed expertise over decades. American industry possessed such depth that non-specialized manufacturers could produce critical aircraft components by leveraging general manufacturing capabilities. The hydraulic systems demonstrated similar principles. Every fitting used standardized threads. Every valve and actuator was designed as a replaceable module. Field maintenance required no specialized knowledge beyond basic mechanical skills. Japanese hydraulic systems required skilled technicians who understood how to adjust and calibrate complex mechanisms. The Americans had designed adjustment and calibration out of their systems through precision manufacturing. Fuel systems on the B-29 incorporated self-sealing tanks that automatically closed when punctured by bullets or shrapnel. The technology had existed since the late 1930s, but Japanese industry struggled to produce self-sealing fuel cells reliably. American bombers carried protection as standard equipment. Japanese aircraft burned when hit because the technology to prevent fires remained beyond consistent manufacturing capability. The psychological impact on Japanese engineers examining the wreckage proved as significant as the technical discoveries. These were men who had devoted their lives to aeronautical engineering, who had designed aircraft that had dominated Pacific skies early in the war. They understood that the B-29 represented not just superior engineering, but systematic American advantages that made Japan's defeat inevitable. The bomber was proof that industrial capacity ultimately determined modern warfare outcomes, regardless of courage, skill, or tactical brilliance. By August 1945, when atomic bombs dropped on Hiroshima and Nagasaki ended the war, Japanese engineers at Yokosuka had documented thousands of pages of technical notes on the recovered B-29 components. The information arrived too late to influence Japanese aircraft development. The examination's real value would emerge in the decades following Japan's surrender, when those same engineers applied lessons learned from studying American technology to rebuilding Japanese industry on entirely new foundations. The occupation of Japan began officially on August 30th, 1945, when General Douglas MacArthur arrived at Atsugi Airfield aboard a Douglas C-54 transport named Bataan. Within weeks, American technical intelligence teams fanned across Japan's industrial landscape, documenting what remained of the empire's war production capability. What they discovered was devastation so complete that initial assessments questioned whether Japan could ever rebuild as an industrial nation. Factories lay in ruins, their machinery destroyed by bombing or sabotage. Transportation networks had collapsed. The skilled workforce that remained was scattered, demoralized, and starving. Yet, among the rubble, American engineers found something unexpected: a population of highly educated, technical personnel whose understanding of their own defeat was far more sophisticated than their conquerors had imagined. The engineers who had examined the recovered B-29 components at Yokosuka were among the first Japanese technical personnel interviewed by American intelligence officers in the autumn of 1945. Major Robert Harrison, a mechanical engineer from Detroit assigned to the United States Strategic Bombing Survey, spent 3 weeks interviewing Dr. Takeo Doi about Japanese aircraft engine development. Harrison expected to encounter denial or face-saving explanations for Japanese technical failures. Instead, he found an engineer who understood exactly why Japan had lost the industrial war and could articulate the lessons with brutal clarity. "We knew by 1944 that we could not win," Doi told Harrison through an interpreter. "Every captured American component we examined told us the same story. Your industry could produce, in 1 month, what took us 1 year. But, more important, your production methods meant your aircraft worked as designed. Ours required constant adjustment and repair. We were not defeated by better pilots or braver soldiers. We were defeated by better manufacturing systems." Harrison's interview notes, preserved in the National Archives, reveal the depth of Japanese engineering understanding. Doi had calculated approximate B-29 production rates based on serial numbers observed on components from the wreckage. His estimates proved remarkably accurate. He understood that Boeing, Martin, and Bell were producing the bombers on parallel assembly lines, using interchangeable components manufactured to standardized specifications. He recognized that American production methods represented a fundamental approach to industrial organization that Japan had never implemented systematically. What surprised Harrison most was Doi's insistence that Japan's defeat held valuable lessons for the future if Japanese engineers could set aside national pride and learn from their conquerors. Other interviews conducted by the Strategic Bombing Survey Team revealed similar patterns. Commander Jiro Horikoshi, the Zero fighter designer, spent hours explaining to American interrogators how Japanese aircraft production had relied on skilled craftsmen who individually fitted components to each airframe. He described visiting the Mitsubishi plant at Nagoya in 1944 and watching workers hand-form aluminum panels over wooden molds, a process that would have been automated in American factories using hydraulic presses and steel dies. "I understood then that we had organized our industry for peacetime production of hundreds of aircraft," Horikoshi explained. "You had organized yours for wartime production of hundreds of thousands. The gap was not technical knowledge. It was industrial philosophy." Captain Shiro Kawamoto, who had led the structural analysis of the B-29 wreckage, provided American engineers with detailed documentation his team had compiled. Page after page of technical drawings, measurements, and observations filled notebooks that Kawamoto had hidden from potential destruction in the war's final weeks. American engineers examining these notes were struck by their accuracy and thoroughness. Kawamoto had understood principles of automated production, standardization, and systems integration that some American engineers assumed were trade secrets. The Japanese had not lacked knowledge. They had lacked the industrial infrastructure and capital investment to implement what they knew was theoretically possible. The Strategic Bombing Survey's final report on Japanese aircraft production, published in 1946, concluded the bombing had been devastatingly effective not because it destroyed production capacity entirely, but because it disrupted a production system already operating at the limits of its capability. Japanese aircraft factories depended on networks of small subcontractors providing components. When bombing severed those networks, production collapsed because the system lacked the redundancy and standardization that might have allowed rapid adaptation. American factories, organized around interchangeable parts and multiple source suppliers, could route around disruptions. Japanese factories could not. The difference reflected fundamental approaches to industrial organization, not just different scales of production. Yet, within this devastation lay the seeds of transformation. The American occupation authorities faced a strategic decision about Japan's industrial future. Some voices advocated keeping Japan economically weak, preventing any resurgence of military capability. Others increasingly concerned about Soviet expansion in Asia argued for rebuilding Japan as a stable, prosperous, democratic ally. The latter view prevailed. By 1947, occupation policy shifted toward economic reconstruction. Japanese engineers who had studied American technology during the war suddenly found their knowledge valuable in entirely new contexts. Dr. Doi joined a consortium of former aircraft engine manufacturers, reorganizing to produce industrial machinery and automobile engines. The precision manufacturing techniques he had observed in the Wright R-3350 engine components could be applied to commercial products. Tolerances that had seemed impossible to achieve during wartime could be approached systematically with proper investment in machine tools and training. Doi spent 5 years helping establish production standards and training programs that brought Japanese manufacturing precision up to international levels. By 1952, Japanese factories were producing diesel engines for ships and generators with reliability comparable to American and European products. Commander Horikoshi, the Zero designer, found work with a trading company that imported American machine tools and manufacturing equipment. His role involved explaining to Japanese factory managers how American production methods could be adapted to Japanese conditions. He wrote extensively about manufacturing philosophy, arguing the Japanese industry needed to abandon its reliance on individual craftsmanship in favor of systematic quality control built into production processes. His articles, published in Japanese engineering journals throughout the 1950s, influenced a generation of manufacturing engineers who would transform Japanese industry. Captain Kawamoto joined Toyota Motor Company in 1947, bringing his understanding of American production methods to automobile manufacturing. Toyota's founder, Kiichiro Toyoda, had visited American automobile factories in the 1930s and understood mass production principles, but implementation had proven difficult in Japan's pre-war economy. Kawamoto and others like him, returning from examining American military technology, brought fresh insights into how systematic production could be achieved even with limited capital. They understood that precision tooling, standardization, and quality control systems could substitute for sheer scale. A smaller factory, properly organized, could achieve efficiencies that larger but poorly organized facilities could not match. The transformation took decades. Japanese factories in the early 1950s still relied heavily on skilled manual labor. But systematic changes were accumulating. Companies invested in precision machine tools, often imported from America or Europe. Training programs taught workers statistical quality control methods developed by American statistician W. Edwards Deming, who visited Japan in 1950 and delivered lectures that profoundly influenced Japanese manufacturing thinking. Production systems evolved to emphasize continuous improvement, waste reduction, and defect prevention rather than defect detection. Every change reflected lessons Japanese engineers had learned by examining American products during the war. Toyota developed the Toyota production system through the 1950s and 60s, creating manufacturing methods that would eventually be studied worldwide. The system emphasized just-in-time production, minimizing inventory by coordinating supplier deliveries precisely with assembly requirements. It implemented quality control at every production stage rather than relying on final inspection. It empowered assembly line workers to stop production when defects appeared, preventing bad components from advancing through the system. Every principle reflected a sophisticated understanding of how to achieve quality and efficiency systematically, rather than depending on skilled workers to compensate for poor processes. By the 1960s, Japanese manufacturers were producing consumer electronics, cameras, and motorcycles that competed successfully in international markets. Sony, Honda, Yamaha, and Canon became recognized brands. Their success was based not on copying American designs, but on implementing production methods that ensured consistent quality. Japanese engineers had learned from examining American military technology that modern industrial competition was won through superior manufacturing systems, not just superior designs. They had spent 20 years implementing that lesson across Japanese industry. The irony was not lost on older engineers who remembered the war. Kawamoto, in an interview published in 1974, reflected on his experience examining the B-29 wreckage 30 years earlier. "We were studying the weapon that was destroying our cities, trying to understand how to defend against it," he recalled. "What we learned, instead, was how to rebuild our country after the war ended. The Americans defeated us militarily, then showed us how to become their economic competitors. I do not know if they understood what they were teaching us." Kawamoto retired from Toyota in 1978, having helped establish production systems that made Toyota one of the world's most efficient automobile manufacturers. The human cost of the lessons learned during the war remained immeasurable. The B-29s the Japanese engineers had studied so carefully had killed hundreds of thousands of Japanese civilians in firebombing raids. The industrial capacity those bombers represented had crushed Japan's military forces through sheer material superiority. Young men like Lieutenant Commander Shibata, the Zero pilot, who had described attacking B-29s as throwing stones at armored vehicles, had watched friends die in aircraft that were obsolete before they left the factory. The engineers examining American technology had known their own weapons were inadequate, but lacked the industrial means to produce better ones. The knowledge had been worthless during the war. After the war, that same knowledge became the foundation for transformation. Engineers who had measured rivets and documented production methods in captured American aircraft became architects of Japan's industrial rebirth. They had learned viscerally that modern manufacturing required systematic organization, precision tooling, interchangeable parts, and quality built into processes rather than inspected in afterward. They had seen these principles implemented in weapons that had defeated them. They spent decades implementing the same principles in products that would make Japan an economic powerhouse. By the 1980s, when American automobile manufacturers faced intense competition from Japanese imports, American engineers toured Japanese factories to learn efficiency techniques. The reversal seemed complete. Companies like General Motors and Ford studied Toyota's production methods, trying to understand how Japanese manufacturers achieved quality and efficiency that American factories struggled to match. The irony cut both ways. Japanese engineers had learned mass production from examining American products during the war. American engineers were now learning refined versions of those same principles from the students. The B-29 Superfortress dropped over 170,000 tons of bombs on Japan during World War II, more than any other aircraft type in the Pacific Theater. The bombing campaign destroyed over 40% of Japan's urban areas, killed hundreds of thousands of civilians, and shattered the industrial base that had supported Japan's war effort. The aircraft earned its place in history as one of the most effective strategic bombers ever built. But perhaps its most profound impact came not from the destruction it delivered, but from the lessons it taught when Japanese engineers examined wreckage recovered from Tokyo Bay in the spring of 1945. Those engineers discovered that American industrial power stemmed not from superior materials or more talented designers, but from superior organization of manufacturing processes. They learned that standardization, precision manufacturing, interchangeable components, and systematic quality control could achieve what individual craftsmanship alone could not. The ability to produce complex machines rapidly, reliably, and in quantities limited only by available resources. The lessons learned from studying enemy technology during wartime became the foundation for peaceful economic competition during the post-war decades. The captured B-29 components, examined at Yokosuka, were eventually scrapped or lost during the chaos of Japan's surrender. No complete record remains of all the technical documentation Japanese engineers compiled during their examination. But the principles those engineers extracted from studying American manufacturing methods survived in their minds and in the industrial systems they helped build during Japan's reconstruction. The transformation of Japanese manufacturing from craftsman-based production to systematic mass production represented the final validation of principles embodied in that recovered bomber wreckage. The story that began with salvage divers retrieving wreckage from Tokyo Bay in April 1945 ended decades later, with Japan and America as allies and trading partners, competing economically while cooperating strategically. The examination of captured American technology had taught Japanese engineers that their wartime defeat was inevitable given the industrial capacity gap. More importantly, it taught them why they had been defeated, and in understanding the reasons for defeat, they learned how to ensure that industrial inadequacy would never again limit Japan's capabilities. The lessons were purchased at tremendous human cost, learned through national catastrophe, and implemented through decades of disciplined effort. Engineers in manufacturing programs today study the transformation of Japanese industry as a case study in how examining competitors' products can reveal invisible systems and methodologies. They learn that understanding an opponent's methods matters more than copying their designs. They discover that principles of production ultimately determine outcomes of industrial competitions, whether military or commercial. The story demonstrates that defeat, properly understood, can become the foundation for transformation, and that lessons learned from enemies can prove more valuable than victories won over them. The Boeing B-29 Superfortress served as both destroyer and teacher, weapon and textbook, instrument of defeat and catalyst for rebirth. Japanese engineers who examined its wreckage with defeat fresh in their memories spent the remainder of their lives applying what they had learned to building a peaceful, prosperous nation. They had studied the technology that had burned their cities, and from those ashes had extracted principles that would make Japan an industrial leader. The bomber's most lasting contribution to history was not the destruction it delivered during the war, but the transformation it inspired in the decades that followed. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.